This is a video for AQA Further Pure Mathematics, Sequences and Series Section 2.1, where we're going to introduce the idea of mathematical induction. Well, firstly, I'd like you just to pause the video at this stage and to do the calculations on the screen and decide what you think the next two terms will be. So pause now, and then when you've done that, start again. Well, I hope you managed to get these results so that the sequence that we have is 1 over 2, 2 over 3, 3 over 4, 4 over 5. So we'd probably expect, I hope, that the next ones would be 5 over 6 and 6 over 7. So in general, we might say that we appear to have n over n plus 1. But of course that's not proof. We've checked a few examples. It seems to be that they all follow this pattern, n over n plus 1, but we can't possibly check every single example, and that's what we would need to do if we were to use this sort of method. Now with something like this, there are an infinite number of them, so that's not possible. So it doesn't matter how many that we check, then we still haven't got a proof that they are all going to follow the same pattern. We might be fairly confident, however, it's certainly not a proof. Well, let's consider some methods of proof that you have already or may already have met. There is the possibility that we can check every single possible number or value and check that it does follow. So, for example, if we're trying to prove that 97 is prime, we could check through all of the numbers to see if any of them are factors. So therefore, once we've done that, we've checked all cases, and therefore we've shown that 97 is prime. Another method is one where we're using deduction, so we're using a series of deductive steps from things that we know to prove a result about something else or another result. And then there's one that you may have met, which is the idea of proof by contradiction. So this is where we assume the reverse of the result and then lead to a contradiction. This is one which you may have met, particularly when we're trying to show that root 2 is irrational, and we prove it by assuming first of all that it's irrational. In other words, that root 2 is equal to a over b, where a and b are integers. But we prove that that leads to a contradiction, and therefore root 2 is irrational. So those three methods are ones that you may have met before. Now, our assumption that this is equal to n over n plus 1 we certainly can't do by checking every single number, because we don't know that there's another one which might be just around the corner, as it were, that is a counterexample. It's not a straightforward proof by reduction, although in an early video you may have seen it proved using method of differences, but now we're going to consider a new method. That method is known as proof by induction. An analogy for proof by induction is the idea of a row of dominoes stretching off into infinity, so a row which is infinitely long. And what do we need to do to knock all of them down? Well, basically with dominoes, two steps. One is to make sure that if we knock a particular domino down, let's say this one here, then it knocks the next one down. So there we would say we've looked at the kth domino in the line and we're knocking down the k plus 1. So that's the first step. And then the second step is simply to make sure that we knock down the first one. And if we've got those two steps, the first one is going to knock the second one, is going to knock the third one, and so on. So all of these dominoes get knocked down. So that's the analogy. When it comes to proving a result by induction, we follow the 3 steps in our so mathematical induction. Step 1 says show that it's true that for any individual number, then it is also true for the next one. So this would be to say that if it's true for n equal to k, so if true for n equal to k, then that implies it's also true for n equal to k plus 1. The second step is then to show that it's true for n equal to 1, so we show true for n equal to 1, and then we put those 2 things together to make a concluding statement, so that it must therefore be true for all integers greater than the first one, so greater than or equal to the first one. Now when it comes to it in practice, we tend to change steps 1 and 2 round, so we usually do the n equal to 1 before we do what's called the inductive step, which is fine with the mathematical one. Of course it's not going to work with the dominoes. We've got to check that all of those dominoes are going to fall down first. Well, the first step is to show that the result is true for n equal to 1. So we do that simply by substituting 1 into our formula. S1, we can see at the top, is just equal to 1 over 1 multiplied by 2. And therefore that's equal to 1 over 2. And indeed that is equal to 1 over 1 plus 1. So our formula, which is n over n plus 1, is true for n equal to 1. The next step is to assume that it's true for n equal to k. So that, in other words, we assume that sk, which is from S1 all the way up to 1 over k plus k plus 1 multiplied by k, is indeed equal to k over k plus 1. So we assume that that is true. And then once we've made that assumption, we then want to see, well, how does that give us a result for n equal to k plus 1? Well, we can see that sk plus 1 is, as written down there, it's all the way up to 1 over k plus 1 and k plus 2. But we can see that this first part here is just equal to sk. So sk plus 1 is equal to sk plus 1 over k plus 1 multiplied by k plus 2. But we can now use our formula for sk that we are assuming to be true. So this is then equal to k over k plus 1, and then plus that next term, 1 over k plus 1 k plus 2. Right, so to combine those we need to write them as a single fraction which has got a denominator of k plus 1 multiplied by k plus 2. So therefore on the top line we'll get k multiplied by k plus 2, and then from the second term just plus 1. So working out what we've got there, on the top line we've got k squared plus 2k plus 1, and then k plus 1 k plus 2. But the top line you'll see there is k plus 1 all squared. k plus 1 and k plus 2. So we can cancel out one of those to give us our answer k plus 1 over k plus 2. Now if you want to really emphasize, then we should really write this as k plus 1 over k plus 1 plus 1 to show that our result is true for k plus 1. And there it is, all written out. As I say, then that final step there, you may just want to emphasize it as being k plus 1 over k plus 1 plus 1. In other words, it's true for k plus 1, n equal to k plus 1, assuming that it's true for n equal to k. I put those things together then, and we can then give our concluding step, which is our conclusion to the result. So we've shown that it's true for n equal to 1, and assuming it's true for n equal to k, it's also true for n equal to k plus 1. And therefore, by mathematical induction, it must be true for all integers n greater than or equal to 1. So mathematical induction, just to go over as a conclusion to the video then, has 3 steps. We check that it's true for the first value. That's usually going to be n equal to 1, although sometimes it might be some other number that we're starting at. And we assume that the conjecture is true for some value n equal to k, and then prove that that leads to it also being true for the next one, n equal to k plus 1. That's what's known as the inductive step. And then a concluding remark saying that as it's true for n equal to 1, and if true for n equal to k, we've shown it's true for n equal to k plus 1, then it must be true for all values n greater than or equal to 1. That's sort of a fairly standard way of writing the conclusion, so you need to almost learn that form of words to put at the end of any proof by induction. That concludes this particular video. In the next one we're going to be using induction to look at some particular results about matrices.